Hello everyone, this is part 7 of the Marconi 6200A microwave radio test set, or MTS as it's commonly known in the industry, scalar network analyzer. Following on from our last discussion, I've set up an experiment with the diode detector, which I spoke about in the previous video, which I've connected to the Marconi test set output. In this case, we've then got a gender adapter to the voltmeter, so we're going to measure voltage that's coming out the detector. Now, interestingly enough, rather than do a sweep measurement across the entire band, and obviously the voltage will be going up and down respectively as it's sweeping across, what I've done a quick plot before making this video. We set up a CW experiment, so rather than starting at a low frequency and sweeping to a high frequency, what we're doing is we're set up a CW source only frequency, and we can input then one single frequency at a time at one level, and then go right the way from 2 GHz up to 20 GHz and see the performance, the DC output, and plot it on a graph. Now, I've made up my own little graph here, which I've done already. And if you remember, in the previous video we talked about the operational window that the test set can work in with regards to the DC conditions that's coming out the detector, depending versus on frequency. And we can see here I've started a plot where we start at basically 2 GHz and go right the way up to 20 GHz, and we have a plus voltage, 0 volts is centre line, plus voltage going vertically upwards, and minus voltage going vertically downwards. And so we started off the experiment at 2 GHz and measured the DC output level, which in this case was minus 234 millivolts. And we then went to 3 GHz, 4 GHz, 5, 6, 7, 8, 9, 10, and the right way up to 20 GHz. And as you can see, the voltage that this detector can perform seems to work reasonably well. A few little peaks and troughs in it, but nothing major, until we get to around about the 13 GHz mark, and then suddenly there's a plummet, quite a substantial plummet, between 13 and 14 GHz, which seems to denote the bandwidth of this diode detector is between 2 and 13 GHz. But anyway, I'm not sure if that's true or not. But anyway, it drops down to a smaller voltage, it goes up again, and then starts to drop off. But the lowest is around about 10 to 20 millivolts. This particular measurement I took was with the RF cable, which is this specialist cable, which is certified up to 18 GHz with just a few dB loss in it. But what I've done for this next experiment, after doing this particular measurement, is I've physically connected it straight to the port on the test set, so we're not having to consider any cable losses. So obviously it's given a minus voltage out. Now, at first I wasn't sure whether the actual diode detector which came out the instrument gave a positive voltage or a negative voltage, but having consulted with the block diagram for the test set, if we look at the diode detector symbology, it shows a negative output, because the diode is facing the other way around to give negative output. So that gives me a bit of confidence, knowing that if we were to employ this diode detector, that it will give a correct negative output, not a positive output. So you know, we've got a chance of something working. So the experiment set up, so if we start at a set of frequency to 2 GHz and then set the RF output on, which is there, and then when we look, we've got 234 millivolts. If we go, we'll do a larger increment. We'll set the frequency, we'll set 5 GHz, it's dropped a little. Set the frequency at say 7 GHz. Excuse me, dropped a little again. Set the frequency at 10 gigahertz. It's gone up a little. We'll say set the frequency at 12 gigahertz. Still just a little change. 13 gigahertz. A slight reduction. And then if we hit 14 gigahertz, this is where the fun starts to happen. Then it drops somewhat. At 16 gigahertz, drops again, but not as wildly as previously measured with the cable. Let's try 18 gigahertz, drops substantially, and then at a frequency of say 19.9 gigahertz, 20 millivolts. So we get something a bit like this, where we start off at the lower frequencies, quite a reasonable margin, a window, and then gets slightly narrower, and then it really falls off. Now it could be that the diode that's in the test set already, the one that's faulty, would have given more of a wider window, operational window, across its entire frequency range. I don't know. That's something that will remain anonymous, because although the technical description for the test set talks about how the microwave chassis works, and obviously gives good useful information, it doesn't tell you what the voltages would be, what's expected at the output of that diode detector. It doesn't tell you what the operational window range is, you know, for RF levels to start and finish at what. So it's quite vague in how that works. So what's expected? So I've nothing to lose really, nothing to lose. I'm going to have some thinking time now. I'm going to look at options that we discussed in the last video with regard to you know, producing the repair perhaps on the diode that's already in the test set, rather than try and substitute it. But I might just try that, see whether that works. Now if I adjust the power level, RF power level, well first of all we'll set it to a frequency like 2 gigahertz, and then set the RF output power, and we'll put it on the variable attenuator. Now if I reduce the RF level, you can see then that the DC voltage coming out of a detector obviously reduces as well, and which is obviously, in this case I'm using a 0 dBm reference for all the measurements that we've made. Now the output of the yigs obviously going to the diode detector are quite high, the signal levels coming into this, so it does need to pick off. It picks off obviously a sniff of the signal directly coupled onto the diode, so in theory it does need to work at low level RF to give a DC output. So that's why I've chosen this test to give 0 dBm, because obviously if I increase that level, the higher that level goes, obviously the more voltage goes out the diode detector until you reach a certain threshold, and then it doesn't seem to give, if anything it's going down now with a higher level, and then when you reduce the level to around about 0 dBm, the level that it seems to peak there. So it may be that the operational conditions of this diode that I've got in replacement might be okay. It certainly performs up to 20 gigahertz, although not as, there isn't a wide window here, so whether the processor on the synthesizer can accommodate that, whether this is a similar response to what the original diode in the test set would give, the diode detector, I'm not sure. It'd be interesting to get some data to see, but obviously, you know, I haven't got that information from the company Marconi as to what this curve's going to look like. So anyway, that's interesting. At least we've confirmed that one, the diode that's already in the test set that was faulty should give a negative voltage out, not a positive, so that's a good indicator. And secondly, the diode detector there does appear to work right up to 20 gigahertz, albeit with a reduced level output. So all I can do is try it and see what happens. I shall also try a repair under the microscope of the original attenuator, and then we can bob that back in the test set then, and put everything back together and see what happens. You know, fingers crossed, tune for maximum smoke and all that, and just hope that we get the damn thing working. Otherwise it's back to the drawing board and trying to get spares somehow. So join me in the next video when we've got the whole thing back together with this diode detector here in circuit, and then we will do some more measurements, and we will see what interesting results we get. Thank you, see you shortly.